Okay, welcome to today's lecture. We last stopped at the multivariate geometric Brownian motion. You remember that we talked about Brownian motion, or the Wiener process. One has to be precise here. The Brownian motion is just the physical process you want to model and the phenomenon you want to model, the Wiener process, and the geometric Brownian motion. Those are two stochastic processes that you can use to model the stochastic behavior of, say, for example, stock prices and stock returns. And one can generalize this to the case of a multivariate stochastic process. So, for example, you have a two-dimensional process, and you want a stochastic process for that, and one example would, for example, be the multivariate Wiener process, the multivariate geometric Brownian motion. So first you start with an n-dimensional standard Wiener process, W1 up until Wn. Those components for their part are one-dimensional standard Wiener processes. They are supposed to be stochastically independent and pairwise stochastically independent. Then it holds that, again, just like with the one-dimensional Wiener process, the increments of the multivariate geometric Brownian motion are, n-dimensional Wiener process first. Those increments are again now normally distributed, but n-dimensionally normally distributed, and you have the zero vector as the expectation and the unit matrix as the variance-covariance matrix of that n-dimensional multivariate distribution. Okay, now in this case here we consider the n-dimensional stochastic differential equation. Again, the change in x in the process is given by a vector m. It's no longer a constant mu, but a vector m times the change in time plus a matrix h times the change of the n-dimensional Wiener process. So the generalization is pretty much straightforward. Instead of a drift constant mu, you are now taking a vector m, and instead of a volatility sigma or a diffusion component, you are taking a matrix H. Then this stochastic differential equation can equivalently be written as xt is x at t0 plus the integral over the drift plus the integral over the diffusion. And in this case, the solution is simply given by x of t equals m t minus t0 plus the square root of t minus t0 h and z, with the z being now not a standard normal distribution but an n-dimensional standard normal distribution. And again, here in this case, the increments are n-dimensionally normally distributed, and you can write it a little bit different here. Instead of just taking h, you set sigma equal to h times the transposed of h, and this again then is the variance-covariance matrix of this n-dimensional multivariate normal distribution. Go here, and if we now look at this n-dimensional process, we assume that we want to model n stock prices. We have the following definition. The multivariate geometric Brownian motion is characterized by the stochastic differential equation. We are taking the logarithm of the stock price, and then the change in the logarithmic price, aka the log return, is modeled as m dt plus h dwt. So it might be an idea to use a multivariate geometric Brownian motion for the logarithmic returns, for the log returns. Now, the log returns are then given by ut, ln s1 minus ln s1t minus 1, and so on. And because we are using a geometric Brownian motion for the log returns, we can see that again the log returns are now n-dimensionally normally distributed. And we can again see that in many cases, in many models in finance, where we are using a multivariate normal distribution, we are not assuming a normal distribution, but instead we assume a geometric Brownian motion for the process of the prices, and as a result, more or less as a collateral damage, we have the convenient result that the log returns are normally distributed, but we're not assuming them to be normally distributed prices or normally distributed returns, but instead we are assuming a geometric Brownian motion. Okay. Now, I've already told you last time that these are the most basic stochastic processes one can use to model prices and returns. Just using a Wiener process, a diffusion process, where you take a constant mu times the change in time, so you have a time-dependent drift plus a little wiggly behavior introduced by a diffusion component with a volatility parameter. This is the most basic model one can use for as a stochastic process for modeling stock returns. But instead, one can also use jump processes. And for jump processes, this is just the idea that prices, but even more importantly, volatility can suddenly jump. And this is one feature we want to model. And for this, we will be using Poisson processes. Now, the assumption that the financial market values are realizations of continuous processes, because so far we've only looked at continuous processes, is of course not very realistic, because in many cases you will see discrete changes, a sudden jump up or down in prices. In some cases, if we want to model credit default swaps, CDS spreads, those spreads might also suddenly go up €1 or go down 10 cents, and we have discrete changes. Now, for some financial market values or for some prices, the assumption of a jump process can be useful. And the standard example of such a jump process is a Poisson process. By the way, in German we have the same word, Sprungprozesse. Okay, what is a Poisson process with Poisson intensity lambda larger than 0? We have a stochastic process, NT, again, T is larger than 0, and it's called a Poisson process if N0 is equal to 0, so we are starting in 0. NT has right continuous paths. What does that mean? I can explain what right continuous Rechtsstetigkeit means. Yeah?
I would guess that for the upside there might be no jump processes, but on the downside, on the other lines.
You might remember this from school. You might have one function that looks like this, and obviously if the left and the right part are polynomials, for example, the function is continuous everywhere except this jump point. Okay, and the question now is at this jump point is the function continuous? Well, no, of course not, but the question is it continuous in this point, and it is continuous in this point? And if, for example, the function starts at, let's say, this is 1, if the upper part starts at 1, it will be right continuous. The question now is what happens if the function, the lower part, comes from the left and only goes to a certain point in limit, Grenzwert. And then you you can loosen this restriction of continuity by looking at the function from one point to the right and from one point to the left. And then you take the usual definitions of continuity, and you might see that the function is not continuous, but it's at least continuous. It's right continuous or left continuous. So this is much more complicated in stochastic calculus, and even more. You have certain additional properties. For example, one famous and well, it's not famous, but one frequent property is so-called the Cadillac property. It's an abbreviation. Okay, should use my graph. Does anyone know what that means? It's French. It's continuous to the right and limited to the left. It's continué à droite, limité à gauche. And that is why you actually have the accent grave here on the A. So that's Cadillac. And a process, and in many cases you are using processes that have the Cadillac property. You know? We don't need this here, but needless to say that, of course, if you have jumps, you are looking at a function that will never be continuous in all points, but at least it should have this property that it is right continuous, rechtstetig. Yeah?
With regard to the example of the CDS, would this mean that positive company-related news would not affect the upside of the CDS, but negative in terms of jumps, negative?
No. It is not. It is not, and the continuity, the right continuity property is not related to going up or going down. It's related to the fact that you're moving into one direction of time, and into the direction of time it should be continuous. You know? So it can still go up and down, and we will have jumps, but if we move into the direction of normal time, then it should be continuous. You know? It's not a very, for our purposes, it's not that important. You know? But again, in stochastic, you will get the idea that stochastic processes are all about stochastic calculus, forming integrals and forming derivatives of such processes and solving stochastic differential equations. And then, of course, for something to be differentiable, you need continuity. And then these processes have to be Cadillac. Third property, for all n and for all 0, t0, less than t1, and so on. So these are the points in time. ntk minus 1, those are independent. So the increments, the changes in the process, those should be independent, and nt minus ns is distributed according to a Poisson distribution with lambda as a parameter depending on t minus s. So we have a Poisson distribution with a parameter lambda, and lambda is a function of the lag t minus s, so the difference in time between those 2 points. If we are looking at 2 points here, if we are looking at 2 points here, we have t minus s and and t minus s dash, and the lag, the temporal lag between those 2 points is larger in the lower part, and then the parameter will look different because, again, lambda, the parameter of the Poisson distribution, is a function of the lag t minus s. Meaning the distribution can change, but it can only change with respect to the parameter, and the parameter can only change with respect to the temporal lag between 2 points, anywhere in time. So the jump from today to tomorrow will have the same distribution as the jump from tomorrow to the day after tomorrow. But if we are comparing the jump 1 day ahead and 5 days ahead, the parameter may look different. And it will still be a Poisson distribution. Okay, so Poisson processes start at 0. The next slide we can see the continuity property. Process has independent increases or increments, and those increments are Poisson distributed. So this is the proper definition of right continuity. A function is continuous if we have for every, pardon the crappy translation by my student assistants, I have to say that it's a sequence. So if for every sequence xn of the elements of the domain which fulfill that the sequence xn has x as its limit, we have the limit of f of xn is fx. This is continuity. You might have seen this in your introduction to mathematics. There are different ways for defining continuity. And in our case, this is actually equal to the definition of continuity. We have math students here, right? Yeah. Remind me. This property is not equal to the usual definition of continuity in all fields, right? Stetigkeit ist nicht mal gleich Folgenstetigkeit, richtig? Oder ist das äquivalent? Okay. Also in den reellen Zahlen bin ich mir sicher, dass es immer äquivalent ist. Aber, also deswegen, in unseren Fällen jetzt hier würde ich sagen, Folgenstetigkeit, Stetigkeit. Also ich bin gerade überlegen, ob es irgendwelche pathologischen Beispiele gibt oder irgendwelche Räume.
Ich glaube, in Nahräumen ist es auch.
Ja, also ich würde mich jetzt auch tippen. Also wenn sind das nur irgendwelche Sachen, die weit später nach dem Studium irgendwann nachkommen. Ja, also ich hätte jetzt auch gedacht, in den üblichen reellen Zahlen, auch in den komplexen Zahlen, ist Folgenstetigkeit nur Stetigkeit. Vielleicht kurz auf Deutsch, damit das alle nochmal ganz kurz verstehen. Ich habe beispielsweise in meiner Matheausbildung an der Uni, in der Mathematik für Wirtschaftswissenschaftler, von einer Wirtschaftswissenschaftlerin, Stetigkeit so erklärt bekommen, wenn die Funktion keine Sprungstelle hat, ist es stetig. So, das ist natürlich so die Lieschen-Müller-Erklärung für Stetigkeit. Sie haben vielleicht in der Matheausbildung hier bei uns, bei den geschätzten Kollegen des Mathematischen Instituts, das sauber definiert und erklärt bekommen. Stetigkeit ist, Sie können Stetigkeit mit dem Epsilon-N0-Kriterium können Sie das definieren und dann sehen Sie eben Stetigkeit, ja, hat damit zu tun, dass die Funktion keine Sprungstelle hat, ja, aber sauber machen Sie es eben über eine saubere analytische Definition. Und eine äquivalente Definition ist die sogenannte Folgenstetigkeit. Und das war gerade eine Diskussion. Wir haben nämlich gerade überlegt, wo gibt es das denn eventuell nicht? Mir fällt jetzt nichts ein. Deswegen sagen wir jetzt mal, für unsere Zwecke ist Stetigkeit auch immer äquivalent zur Folgenstetigkeit. Und Folgenstetigkeit heißt einfach, wenn Sie Werte auf der x-Achse haben, eine Folge, und die strebt gegen einen Wert x, und Sie setzen all diese Werte in die Funktion ein, dann muss immer gelten, dass auch die zugehörige Folge der Funktionswerte gegen diesen Funktionswert f von x strebt. Ja? Und das ist die Folgenstetigkeit. Und dann sehen Sie nämlich genau, was damit gemeint ist, dass einfach, wenn Sie sich mit immer kleineren Schritten auf der x-Achse einen Punkt nähern, dann müssen Sie sich auch auf der y-Achse mit immer kleineren Schritten genau dem zugehörigen Funktionswert nähern. Und dann kriegen Sie diese Eigenschaft, dass die Funktion keine Umstände besitzt. So. Das ist die Folgenstetigkeit und unten sehen Sie nämlich, was Rechtsstetigkeit bedeutet. So, right continuity. A function is right continuous if we have for every sequence xn of elements of the domain, so usually the real numbers, which fulfills xn are larger than x, and the limit of xn is x, that also again the limit of the function values is f of x. So the difference is just we don't have any sequence, but we are taking sequences that now come from the right. And we could also define left continuity with sequences that come from the left. And now imagine how this would look on the real plane. You would simply take a point x, you would look at the point f of x, and then for continuity, it doesn't matter if you're coming from the left or the right, and closing in on x would mean that you're closing in on the function value of x, and right continuity is just this split up. And I would pretty much assume from this definition that if a function is left continuous and right continuous at a point, it's also continuous. Rechts- und Linksstetigkeit sind natürlich gemeinsam zusammen nachher die übliche Stetigkeit. Okay. Und nebenbei wenn Sie so eine Funktion haben, dann können Sie nämlich genau damit hier Links- und Rechtsstetigkeit sich dann anschauen. Die Funktion ist offensichtlich nicht stetig, aber was ist sie denn? Wenn Sie Sie gehen, von links kommt immer zu einem Punkt, ja, und dann springt es und dann haben Sie, meine ich, Linksstetigkeit. Nicht? Nee, rechtsstetig? Rechtsstetig, okay. Sehen Sie mal. Für sowas bin ich immer dankbar. Mein Mathestudium ist schon mehr als 12 Jahre, liegt das schon zurück und ich denke mir immer, es ist mehr als meine gesammelte Sammlung an BWL-Professoren überhaupt jemals machen konnten. Auch keine algebraische Gruppe von einem Körper unterscheiden. Also da bin ich dann trotzdem froh, wenn ich dann ab und zu mal so ein paar simple Fehlerchen mache. Gut. Characteristics of Poisson processes. Those are partly constant, which makes sense because we are staying constant, and then suddenly the process can jump up or down. They are monotonically non-decreasing. They show upward jumps of the height 1, so they jump with this step 1. And they have an exponential distributed waiting time, and the waiting time is the probability of capital T larger than t, and this is the exponential function with this Poisson intensity lambda as a parameter. And t is the waiting time until the next jump. Now, on the next slides, you will see a lot of MATLAB code, and here this is programmed with very much detail. So we want to simulate one path of the Poisson process. We need lambda, the Poisson intensity, the number of jumps, the starting value, the number of paths, and we want to avoid the output on the screen. So we set this parameter here. We initialize the jumps with zeros. We are assigning the starting value in the first, and this is the first column, and then we have the corresponding values. And now what we do is we know that the jump will take the process from 0 to 1, from 1 to 2, from 2 to 3, and so on. The only thing that is stochastic is the waiting time, the time we have to wait until the next jump goes from 2 to 3, 3 to 4, and so on. So the waiting time until the next jump is distributed according to an exponential function, and you can see that here we are calculating the time, and then we have the graphic output. This is just for printing the paths on the screen, and we're using with the stairs. And we are using a number of certain parameters. And this here, these are two paths of the Poisson process with intensity 2. You can see that actually the step is always 1 up, and the only thing that is different here is, okay, no, that we have to wait. Here we have to wait a little bit longer, and you can see here, it's the second process. Actually, it might also be that both cross, and that now the second path is above the first one. That's nice, but it's still not very practical when it comes to modeling jumps in volatility or CDS spreads. Now, where can we use these Poisson processes? They are actually quite common in insurance mathematics and in actuarial science. You can model the occurrence, not arising, the occurrence of insurance losses. In medicine, you try to model clinical deaths. In IT, you can model the arrivals of tickets. For example, if you call our IT service here at the university, you will get a ticket and it will tell you, okay, your request is being handled under ticket number 2050, and please in all future correspondence refer to this ticket number. And of course, you need to model the occurrences of these jobs and these tickets. And in corporate finance, you can try to model sales on a stock exchange and transactions. Problem is, the Poisson process doesn't look like a stock price at all. But the trend of the share prices is similar to the already known geometric Brownian motion, which is also used in the Black-Scholes model. So what do? You simply take the Poisson process and you add it and you integrate it into the geometric Brownian motion. So this is the main idea here. Remember, this was the geometric Brownian motion with drift 0.1 and volatility 0.3. Looks pretty much like, could be the stock price. And we now want to include a jump component. Now, what we are doing now is we are taking the geometric Brownian motion, that is mu, the drift times the process itself, st dt plus sigma st dwt, and we add a jump component. So it becomes a jump diffusion process. So the diffusion component can jump, and this is called a jump diffusion process. So dst, the change in the stock price, is given by the previous drift, mu st dt plus sigma st dwt plus st djt, the change in the jump process. And jt is described by simply the sum of all xi, whereas nt is a Poisson process and xi are independent, identically distributed jump heights. And jt is also called an aggregated Poisson process. In explicit notation, this jump diffusion process can be written as st is equal to st 0 times exponential function and so on. And you can see that in the end you have this difference in the jump process. And if you discretize this, discretize this, a discrete path would look like this here. And again, from this formula, you can see that you can easily simulate a path of this jump diffusion process. So if you do this in MATLAB, again, you need a starting value, but you now also need a drift, you need a volatility, you need a jump intensity, the level of detail of the grids, and the number of points on the x-axis, the number of paths you want to simulate, and is quite simple, actually, if you know the formula. You simply take the formula for the discrete path of the jump diffusion process, but you need to code all this in MATLAB, and you can see that you first have to initialize the J path with a zero matrix, it's a matrix, and then you have to assign the start values, you have to discretize the steps, then you need mu t, you need sigma dt, and then you simulate from the Poisson process. You're using the function we've defined earlier, and then you have to adjust it. You have to cut the Poisson process after n steps, and then you need to put them on the grid and to calculate those changes in the jump diffusion process and simulate it and print it on the screen. And this is these are the parameters used. Again, mu 0.1, sigma 0.3, but now with an additional diffusion, jump diffusion component. And these are two processes and two paths from this jump diffusion process. Yeah. Now the question is, do we really see a difference here? Do you see a difference in comparison to the geometric Brownian motions? Well, I wouldn't say that there is a difference visible here on this part, but it would be interesting to look at the returns. So in the returns, you would probably see a slight difference. So you are now looking at the actual process, and you would need to look at the differences, discrete returns, or more likely the log returns, and then you should see a difference compared to the geometric Brownian motion. Okay. Now, financial mathematics is nowadays full with even more complicated and more clever types of processes that can be used to model stock prices and stock returns. Why? Well, quite simply because one can argue that even the jump diffusion processes are not flexible enough to account for all those empirical stylized effects on prices and returns. And if you have the impression that your model is not flexible enough, you come up with more insightful ideas what you can further include in this process. The processes will become more complicated, they will become more difficult to handle later on, and in the end you will have a stochastic process. You will prove that you can simulate from this process, that it has certain properties, and then you will, well, what will you do? Later on we'll see that in the Black-Scholes model and in option pricing, one important problem is that in the basic case of the Black-Scholes-Merton model, you are assuming a Brownian motion. Then you have an analytical formula for the option price. You get a formula, and you might know this from previous lectures. Option price is equal to blah, blah. But as soon as you use a different process that is more complicated, for example, a jump diffusion process, this result no longer holds, and the Black-Scholes-Merton model cannot be, the Black-Scholes-Merton equations cannot be solved. And what you need to do is, you need to simulate from these processes and just solve it by brute force. Instead of using clever calculus and stochastic calculus to solve it, you see that you cannot solve it for a formula, then you just put in a lot of computer effort, you simulate a lot of numbers, and then you put all those simulated paths into the model and look what the option price would look like under these scenarios, more or less. And that is why, in the end, computational finance is synonymous to this work that has been done on stochastic processes with applications in option pricing. Yeah? It's all about coming up with new processes, simulating from these processes, and fine-tuning these processes in order for the simulation to be able to run on a computer. And sometimes you need a grid. You know? And it's why it's computational, because this might, if the models get too complicated and too detailed, you will need a lot of computer power to solve for these equations or to simulate from these processes, and then you need a lot of computer power. And everything that will help reduce the computational effort and the computational burden will help you get a better estimate of the option price. Okay. Now the delta normal method. We've seen that the multivariate geometric Brownian motion leads to a multivariate normal distribution of the log returns. And in the following, we just want to shortly address the question, what can we do with it? If we are assuming geometric Brownian motion for a set of risk factors, then we know that these risk factors, let's call them Z1 to Zm, these m risk factors will be multivariate normally distributed, and this makes it quite simple to estimate the value of risk of this risk portfolio. So if we have m risk factors, if we have a portfolio or a certain asset J, the value of the asset J will be a function in these m risk factors. So Vj is a function and the jth function of the risk factors Z1 to Zm, and the change in the value will be Vj minus Vj at points t plus h and t. So after some simple calculations, you realize the same result we also get in the bachelor's class on risk management, that actually for risk modeling it suffices to look at the changes in the risk factors. So if you're interested, for example, in the risk of an interest-bearing asset, you need to look at the changes in the interest rates. So we're interested in the calculation of the valued risk of this random vector v1 to vn. Those functions, these are called risk mappings of the risk factors to the performance of the portfolio, to the price of these single assets, and they can be determined by a first-order Taylor approximation. Does everyone remember or know what a Taylor approximation is? Linear order Taylor approximation. Taylor theorem says what? No one? Okay. If you have a function and you take a point A, and you have a function that has certain properties, for example, is differentiable, Taylor's theorem tells you that in a however small or large vicinity, in an unknown vicinity of this point A, so for example in this interval, the function f of x is equal to the Taylor series, Taylor I. And the Taylor series is given by what? An infinite sum of polynomial terms that include the derivatives of the function in its components, its coefficients. Meaning that, in fact, any function that is differentiable and has some other properties can be expressed as a polynomial in a vicinity of this point A. Unfortunately, you don't know how large this this vicinity is, and this is not the world formula, but still you know that at this point and in this point the function can be expressed as a Taylor series. Now, what is a Taylor approximation, a first order Taylor approximation? You simply take this polynomial and you cut off all those higher order terms, and as you probably know, a polynomial is what? It's a constant plus a linear term plus a squared term plus x raised to the third power and so on, and you simply leave out those higher order terms and you have a function that is linear. So in other words, from derivatives, you know that you would simply use in this point a linear function that approximates the function. This is more or less the idea of a first order Taylor approximation. A second order Taylor approximation would then of course include a term of x raised to the second power, so x squared and so on. And because this is a linear approximation, a linear function that we are using, we are also calling this a linear approximation. And then if we take this function, this risk mapping f1 to fm is given by a first order Taylor approximation, so it is just the change in the risk factors multiplied by the partial derivatives of those risk functions, those risk mappings with respect to the individual risk factors. This looks pretty generic and not very intuitive, but remember and see that this again comes from option price. We have a function, or we have a position, an option. We are interested in the change in the value of this position. The change in the value is a change in the price. The price is what? It's, for example, given by the Black-Scholes formula. And if you are interested now in the risk mapping, you can see that the risk mapping is given by some partial derivatives times change in the risk factors. And what are those partial derivatives? Those are in the Greeks from the Black-Scholes model. Partial derivatives of the option price with respect to the risk factors. So, for example, it could be the option delta, the option rho, the option beta, and the option gamma. Those are the Greeks, and this is again why Greeks are so frequently used in practice, because if you do a Taylor linear approximation of the riskiness, more or less, of the option position, you simply take the option Greeks, the partial derivatives. Okay. Now, with the related random variables, we get the change in the value is given by here the sum of the changes in the risk factors times the partial derivatives, for example, the option Greeks. And if the changes in the risk factors are a multivariate, are distributed according to a multivariate normal distribution, we actually get a normal distribution for the changes in the values as well. So as a result, the normal distribution of the risk factors transgresses into a normal distribution for the changes in the values, in the prices. And this, it looks trivial, but for a modeling purpose, I think it's interesting and important to understand what is going on here. If you take a textbook, if you take a business textbook on risk management and on option pricing, you will probably just see that we are assuming a multivariate normal distribution for our losses, or for our P&L, our profits and losses. But in fact, it's a little bit more complicated. What you are doing is actually, first of all, you need to assume that the losses and the profits and losses of your positions, they don't fall from the skies, but they are actually the result of a risk mapping. Meaning that you need to have some idea how those risk factors, interest rates, prices, default probabilities, and so on, how these risk factors come into play and make a position earn or lose money. Now, with a stock, this is quite simple. For a stock, you would simply take the price and the code of the stock as the single only risk factor, and it's very simple risk mapping. But take options. The option price is a function of the interest rate, the risk-free rate, the volatility, the current stock price, and maybe some additional risk factors, but usually just maturity, risk-free rate, volatility, and current stock price. But, as you might know, the Black-Scholes-Merton model, the formula is not as simple as, for example, just 1 plus R times 100, or something like that. So you have a risk mapping, and the question then is, do you simply assume that this risk mapping is linear? No, but you are making the simplification that you can take the risk mapping and in first order approximation, it becomes a linear function. And by coincidence, because you're using a Taylor approximation, you get the partial derivatives of the pricing function as the coefficients of this linear approximation. And those partial derivatives are the Greeks from option pricing. And then you're not assuming a normal distribution for those risk factors, but in fact, in many cases, you're assuming a geometric Brownian motion for the log returns, for example, for stocks. And then, if you assume a geometric Brownian motion, you get log returns that are normally distributed. And last thing you need to remember that the normal distribution is how do you say this in English? Is the normal distribution doesn't change under linear transformations. It's invariant to linear transformations, meaning that if you have a random variable x and you put x in a linear function, and you have a function y that is a linear function of x, y is also normally distributed. So if you have x and, for example, you have y defined as, this is again normally distributed with some other parameters, or if you have x and y normally distributed, x plus 3 times y, all these transformations are again, or yield again, a normal distribution. And it's the same here, just in the multivariate case, that if you are assuming a multivariate distribution for multivariate normal distribution for the risk factors, and you are inserting those risk factors into a linear function, the resulting function, which in this case here are the changes in the prices, the losses, those losses are again multivariate normally distributed. And again, this then shows you that the portfolio has a multivariate normal distribution, and then you can simply calculate the value at risk and the volatility of this portfolio of these positions, which is quite simple. For the normal, for example, for the univariate normal distribution, you can simply calculate the VAR, the value at risk, which is nothing else than a quantile function, the distribution, as mu plus sigma times z quantile, from the standard normal distribution. You might remember this from statistics. And this is the usual approach to calculate the value of risk or another risk measure under the assumption of a multivariate normal distribution for the risk factors and a linear approximation of the risk mappings. And this is frequently done. And you will find this in any textbook on option pricing, on risk management, in which you are you're shown that the value at risk is can easily be computed because, well, it's a normal distribution. But it's a little bit more complicated if you want to understand the mechanics of this modeling. Okay. Any questions so far? Okay. I have to skip the slides now because unfortunately I have to switch to the German ones, and we'll talk. I'll try to translate it just on the fly, which shouldn't be a problem because this is a very simple part. It's about numerical integration and quadrature. Numerical integration is an important part of numerical analysis. And why is that? Because we've already seen that, especially when it comes to stochastic calculus, we need to compute a lot of integrals. We need an integral for the normal distribution. We need integrals for stochastic differential equations. We need integrals everywhere. And to see the importance of this is just the simple example. Imagine that you want to compute the expected value of a continuous random variable. Again, an integral. It's the integral over the whole real numbers of x times the density function of f, and we need to calculate this integral. Even probabilities have to be computed with an integral. You take the density and you will hopefully remember that the density function does not give you probabilities, but it gives you probability densities. And you only get the probabilities by taking the integral between point A and point B, and you get the probability that the function will be between A and B. So we have expected values as integrals, we have probabilities as integrals, and in many cases, nature will not give you nice examples like in high school, where you can nicely solve for those integrals on a sheet of paper, but most of the time those integrals cannot be solved. And you need an approximation to those integrals. Now, it is interesting to see that this is a part where calculus and numerical analysis are quite similar, and actually they have the same starting point. Remember what is an integral. First, remember that integral is not integral. One has to be precise. We are talking about the plain vanilla high school integral. Here, this is the Riemann integral. Now, the Riemann integral is what? It is simply the limit of those Riemann rectangles. And remember that what you do is you are looking at those rectangles under the function, and you are letting the size of those rectangles decrease to 0, and in limit you will get the space under the function. And this is the usual definition of the Riemann integral. However, numerical analysis isn't much different from that. We're using the same idea, just we are not trying to solve it in limit, we are not trying to solve it exactly and analytically, we're just trying to get a good estimate of those spaces under the function. Now, remember, and this is interesting, the integral, the Riemann integral, is a linear operator. Why? It's linear because it's defined as the sum, meaning that if you want to add something, you are adding something to a sum, so it's already a sum of not just n elements, but then it's n plus 1 elements. So it's a linear operator, So it makes sense to approximate the integral with a linear function. And we're starting by dividing up the integration interval into, we're interested in the integral from a to b of function f. And we are cutting this interval into little pieces with x0, x1, x2, and so on, xn. x0 is the first point, xn is the last point. And then the first simple quadrature formula could be given by the approximation of the integral of f is given by sum j starting with 0 up to n of wj weights, that's why they're already called w, weights times function values at point xj. Why? Any idea? What is the idea behind this? I'm looking for some space. Let's assume this is a, this is b. And we're interested in the integral of this function. Now, what could we do? A very simple idea would be x1 and let me get some rectangles. Where's the color? Let's hope this works. Yeah, perfect. And this is a very crude approximation, but nevertheless, this is close to being the space and being the integral. Now, how would these rectangles look like? They would look like, okay, x1 minus a and b minus x1 times what?
The function is at a or b.
Yeah, actually at this point here and at this point here. Right?
Can I see where you're
Here. Here and here.
Alright.
So this is f of x dash, and this is f of x double dash. Let's call them x dash and x double dash. Slightly different to the formula we have down here. So let's correct that. Let's say we want to do it like it is done down below. So we are saying here and here. And here we have actually here f of a and f of x1. So f of a times f of x1. And then you can see that this here is w0, this here is w1, and we have exactly this quadrature formula down below. Weights, those will be usually the distances on the x-axis times a certain function value. But you've already seen that there are certain things you change about this. You take the function value at the start of this interval, or at the end, or in between, at the lowest point, highest point, and everything we do afterwards here just deals with the question, how can we optimally choose those weights and those function values? Those points xj, those are called the nodes, die Stützstellen of this quadrature formula, and w, those are the weights, the quadrature weights. Now, the accuracy of the approximation can simply be calculated by the exact integral minus the approximation. Now, if epsilon is 0, it means the integral is equal to its approximation, and we have a perfect match between our best guess and the integral. However, you don't know the integral. You never know what the integral looks like. But you can do the following. We have already seen that polynomials, if you just go high enough with polynomials, no, actually we haven't really seen that. Yeah, I should explain that first. Perhaps one of the math students can quickly tell me the simple result on polynomials and interpolation. What's the interpolating polynomial? And what does it mean if you are given n points? Nothing. Was ist ein Interpolationspolynom? Ja?
Ich glaube, Sie wollen darauf hinaus, dass wenn man jetzt diese 6 Punkte gegeben hat, dass man, wenn man eine Polynomfunktion der Ordnung 5
Genau.
wählt und die durch diese Punkte legt, dass sie dann einhält.
Yeah. In numerical analysis, you have a very simple result that if you are given, for example, in this case, 6 points, there's exactly one polynomial of order 5 that interpolates those points. You probably know this if you take 2 points. You know that you only need one linear line that goes through 2 points. This is also possible, but if you want to keep the order of the polynomials as low as possible, you can actually do this with a line. If you have 3 points, here, here, and here, you know that it will no longer be able to use a linear line, but you have to increase the order of the polynomial by 1. So in this case, you might, for example, have something like this. And with 6 points, okay, close enough. A very simple result. There's exactly one and only one polynomial of order 5 that interpolates those 6 points. It's quite simple to prove that it has to be unique, and this is a very nice feature. And actually, this feature explains why if you only have enough points, you can always substitute a function with a polynomial. For example, and remember that, how do polynomials look like? They start with a point, they have a line, then you have a polynomial, a parable, and then if you simply increase the terms and the powers of x, you can get something that looks like this. Yeah? So by increasing the order of the polynomial, the function will be extremely flexible. So if you only have enough points, say 50 points, you can interpolate any function, and you can approximate any function. Sounds very great. Problem is, we'll see this later on in the lecture, polynomials have one disadvantage. You know which? They do interpolate, but
They always, at the end of the, or if you go to extreme values of the domain, they tend to take extreme.
they oscillate. Yeah, they oscillate. And for example, if you have function points like this, for example, it will not look like this, but it would rather look like this. And this doesn't really look like the function we are trying to approximate. In the end of the lecture, we'll see that you can solve this. by using splines instead, polynomial splines. Those are just little pieces of polynomials that are glued together, more or less. But at this point, we can see that it is quite a reasonable idea to approximate a function with a polynomial, because if you just have enough points, the function might look like a polynomial. And those points, those points are interpolated. And this is why here, if you want to assess the accuracy of your quadrature formula, you will not be able to talk about the accuracy for all kinds of different functions, but what you do is you are basing your accuracy measure just on polynomials, knowing that polynomials are very simple, they can be highly flexible, but they are also continuous and differentiable, and this is quite simple, and this is why we call a quadrature formula to be of order m if the quadrature error epsilon is 0 for all polynomials of order m or smaller. Meaning that if we have a quadrature of order 3, it means the quadrature can approximate and can estimate integrals for polynomials up to order 3 exactly. So there will be no error for polynomials with x to the third power and plus 3 times x squared and so on. This also means that we are interested in quadrature formulas that have a high order. For example, if we have an order of m equal to, let's say, m is 10, this means that we can approximate a polynomial that is of very high order. And what is your guess? First of all, the order of the quadrature formula. On what is it dependent on? It depends on what? What is the main ingredient you can change to increase the accuracy of your quadrature? What is the main ingredient? If you think back of this example here, what is the main ingredient? And what is the main parameter you can change? You can actively change. Yeah, the way the weights are defined and the way the function values are chosen. But if you have agreed on a quadrature formula, which is the main parameter, and the number of nodes. You see, the approximation here was very crude because we are only using 1, 2, 3 nodes. If we were to use 10, 12, 20 nodes, we would assume accuracy to increase. Now, let's assume we have 10 nodes. 10 Stückchen. What would you expect is the maximum accuracy of a quadrature formula? Meaning that, for example, if it's of order n equal to 10, it will mean it can exactly integrate a polynomial of order 10. So x raised to the 9th power plus blah blah blah. What would you expect? 10 nodes? Optimal highest accuracy of quadrature formula? Can go up to 3n minus 3. So it would be with 10 nodes, we would have order 27. And this is the only differences. This is the only difference between all those different quadrature formulas. It starts very simple with 2n, n, and it can go up if you fine tune it and have most sophisticated programs and formulas. it will go up to 3n minus 3 or 3n minus 2, depending on whether you have an even or uneven number of nodes. This is quite surprising, I think, because one would think that you need to use 500 nodes to get an accurate estimate of the integral. Actually not. You can use just 10, 20 nodes, and this will suffice, depending on the size of the interval, of course. Okay. So let's talk a little bit about some very basic quadrature formulas, and we'll start with the famous Newton-Cotes quadrature. By the names, you can see that actually some of those formulas date back way into the Renaissance. This is Newton-Cotes quadrature formula. So what you do is, first of all, we are using equidistant nodes. So xj is equal to a plus a certain step. So, for example, we start at 5 and then 6, 7, 8, 9, 10. Equidistant nodes. And fj is the function value. So we are suppressing this argument of the function. So fj is just the function value f of xj. Makes it simpler in notation. And instead of the function, we are using the interpolating polynomial. And if we use the interpolating polynomial and equidistant points, we get the Newton-Cotes quadrature formula. And the interpolating polynomial can be expressed with the so-called Lagrange basis polynomials. And those are given here, ij. And then, is everyone clear about basis polynomials and monomials? No. Let's start with the very basics. What is a linear space? A linear space is a space where you have vectors as elements, and where you have vector addition, a vector sum, and a scalar multiplication. You know this from school, that you have vectors being lines in the space, and you can add those vectors and you get a new vector, and you can also scale it times 2 times 0.5, and you can invert the direction, and so on. Polynomials are the same. Those also form a linear space, a vector space. Meaning that if you have two polynomials and you add them, you get a new polynomial, and if you take a polynomial and you multiply it with a real number, you also again get a polynomial. But you remember from high school that that vectors can be expressed as a linear combination of a basis, basis vector. In the three-dimensional real space, this is quite simple. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is simple, the most basic basis of the three-dimensional real space. And you can express any vector as a linear combination of 1, 0, 0, 0, 1, 0, 0, 0, 1. Simple result in mathematics and linear algebra is every vector space has an unlimited number of bases. So you can also use a different basis. And what you can do is you can express any vector with respect to basis A or basis B, and you have to change the basis. Basiswechsel. And this is one example of a basis for polynomials. You know I would say the easiest, the simplest basis for polynomials, that is monomials, and this is in German the Monombasis. 1x, x Quadrat, x hoch 3, x hoch 4, das ist die Monombasis. Jedes Polynom kann als Linearkombination trivialerweise dargestellt werden als Linearkombination der Monombasis. Aber es gibt eben auch andere Basen des Vektorraums der Polynome. Und das ist eine Basis. Das sind die Lagrange-Basis-Polynome. And you can express any polynomial as a linear combination of those Lagrange basis polynomials. And if you do this, you get the following Newton-Cotes formula. The quadrature is given by b minus a times the sum of the weights times the function values. The weights are given as 1 over b minus a and the integral over the Lagrange basis polynomial. And this is quite interesting, and this is common for all Quadrature formulas. First of all, you don't actually need to compute the integral from a to b. In this area of numerical analysis, you usually only consider integrals from 0 to 1. Why? Because you can always take this function and you can do a change of variables and you can transform the variables such that the integral from a to b is equivalent to the integral of a different, slightly changed function from 1 to 0. So we don't need to care about the interval. We can also do this from 0 to 1. This is equivalent. And the second thing that is interesting here is that those weights, if you standardize those integrals to an integration interval from 0 to 1, those weights will always be the same. Those are actually constants. And back then, hundreds of years ago, those mathematicians simply calculated the weights, wrote them down, and if you go to our library, you can find books from the 18th, 19th, even 20th century, before computers, in which mathematicians calculated all weights for those Quadrature formulas. And of course, you can see that those weights depend on the number of nodes you're using. So if you only take one, you have the trapezoid rule. If you take two, you have the Simpson rule, and so on. And those books, they are hundreds and hundreds of pages long. You will see, okay, let's start. Newton codes. N equal to 1. Weights. Until the 10th decimal point, maybe, or 6. I mean, back then, without a calculator, they were happy to calculate 6 or 8 decimal points. Then n equal to 2, all the weights. N equal to 3, all the weights. And back then, if you wanted to calculate an integral, you needed such a book, and you looked up those weights. Someone else calculated for you hundreds of years ago. And this even continued way into the 40s, 50s, and 60s. I wrote my diploma thesis on more accurate Quadrature formulas. I still have printouts of those books from Kronrod, which was a famous Russian mathematician. He published books with those tabulated weights for Quadrature formulas. I think 10 or 12 decimal points. And everything else is the same for almost all those Quadrature formulas. Always the same standardized integration interval. You need to look up those nodes and those weights. In this case, this is trivial because you know if you have an interval from A to B and those are equidistant, you know the weights. But this is another way of changing the formula, more complex and more detailed procedures. They not only use equidistant points, but someone at some point realized equidistant nodes are actually not the best way to do it. It's best to optimize the Quadrature with respect to both the number of nodes, the distances and the definition of the nodes, and then the weights. And usually the weights will follow. And this is the Newton codes formula. You can see from the name, trapezoid rule, that this is what you might have already seen in high school, but it can get a little bit more complicated from that. Okay. I think I'm already out of time. Do you have any questions? Seems you have no questions, then thank you for your attention and see you next time. Thank you.